Nats FM is brought to you by Synedia, the stewards of the Nats Project. Hey everybody, welcome back to episode 6. We have two special guests this week, one returning from last week, Tomasz, and we have another special guest, Neil. Can you please introduce yourself, Neil?
I'm Neil Twigg. I'm a software engineer working on the Nats server.
Awesome, thanks. Yeah. So Tomasz, you alluded to, this week's episode you alluded to last week, which was 210. Has it been released? Both of you? Yeah?
Yeah, it has been. It was. We didn't have any additional delays. So now we can make a deep breath, make this podcast, and move forward.
Yeah, so everyone listening, watching, this episode is all focused on 2.10 that was released for Nats. So very excited to kind of get into this. We're going to talk through the journey a little bit for all through 2.9, which has been a long haul, and we're going to get into the main themes of 2.10 and what groundwork it lays for subsequent releases, and then maybe we'll peek into sort of what's going on in the future. So I'll kick things off a little bit, just to see, what was this journey like? So for context for listeners and watchers, we have 2.9 that was released back in September of 2022. So we have crossed the year mark for a 2.10 release. So it's taken quite a while compared to previous releases. So I'm going to be provocative here, and why did it take so long, guys?
I don't think we could have even possibly predicted some of the issues that we've come up against in the 2.9 branch. We've spent an awful lot of time focused on quality in particular. We've spent a lot of time working with customers, trying to make sure that they're happy, that everything is working to expectation. And also we had a very big backlog of features going into 2.10. There was a lot that we wanted to accomplish. So balancing the two, it's just taken a while. It's just taken longer than I think any of us had really thought it would.
Yeah. So I think, and echoing that, I think there was, the greater adoption of 2.9 over time, the potential use cases, the potential features, the new scale requirements, all of these things have amounted as a backlog. And then we're like, oh, there's a lot of things to do. And as with any good software release, before you kind of get to the, new shiny thing of 2.10, you want to be sure that the current version works and people can be successful with it. So my takeaway as being part of this sort of on the sidelines a little bit has been, we want to get things right. We want to fix issues that come up that are present now, and then we're going to get to 2.10 when we're quite ready for it, but not too earlier, because don't want to ship bad software at the end of the day. So what do you think, Tomasz?
Yeah, and I think that what's worth mentioning is it was not only about 2.10 scope and making sure that 2.10 is stable and new features are working fine and testing that. It was a lot also about improving. It's kind of hidden behind this patch and some amount of patch releases, but the amount of effort was huge amount of effort of the time that delayed the 2.10 or pushed it back was actually the making it much more stable, especially where the ecosystem grows a lot, the adoption grows a lot. So edge conditions that we never seen start to be almost common in some scenarios. And it was not only us fixing the stuff when it popped up, but we also realized that we would love to catch those before others do. So we put a huge amount of effort of many teams actually to establish some different testing environments, testing scenarios, some chaos tests that we mentioned last time. And this is a huge amount of work that was put there on the things that will also be good for all the future releases and increase our confidence. But that as usual, like, writing those tests and the tools around testing and infrastructure for testing, all of this is expensive in time, especially. So I think that it's almost like a hidden feature of 2.10, like the current one, is how much more stable and performant and predictable the current release is, which was happening in the especially recent 2.9 patch releases.
Yeah, for sure. And we'll get to some of those themes in a minute, but just reflecting, and you mentioned this last episode as well, which is the discipline and the approach taken throughout this sort of year-long journey up to 2.10 has really been observing, an issue, writing a test, or figuring out if a unit test or something is not sufficient, what is a maybe different or a new approach that we would have to adopt in order to, observe the issue. It's a distributed system at the end of the day. We have users and customers creating crazy topologies with superclusters and leaf nodes and all this kind of stuff. And it's like, you can't really bake that into a unit test very easily or practically, because it's, in process versus being distributed across a network are two very different things. So I think that the spectrum of tools and testing strategies have dramatically increased over this past year. And the discipline and the amount of time that it takes to kind of make that all work. I know I've been very impressed, observing the team do this. And for those who don't know, at Synadia, we have a whole team dedicated to, as Tomasz mentioned, among the server team and the client team, but we also have this sort of DevX team, as we refer to it, and they're like doing chaos testing and all sorts of crazy distributed systems testing. And a lot of effort has gone into that. So I think it's worth talking about that and acknowledging it, and sort of hopefully people are excited that, going forward, all of the Nats releases are going to have this foundation and quality of testing going into it, which is, I think, awesome. Go ahead.
I mean, at the very basic level, we talk about unit tests, but we don't often talk about just how many unit tests we have. We have hundreds of them. There are hundreds and hundreds of these tests. And, we do always try to distill a problem down when we discover something to the minimal reproducible case. That's always what we're trying to do. We're trying to break something down to what is the actual cause, what's actually going on, and not just trying to diagnose things by what happens. But, it's not necessarily easy to write unit tests that bring up exotic topologies with leaf nodes and things, but we do it. So, the amount of time that we put into writing tests is huge.
Yeah, and the fun part too is I know a couple of people on our team really enjoy fault injection as well. So it's this idea where we have, like, I don't know, some customer topology on certain kinds of hardware, certain kinds of network links, and you're just trying to introduce that little bit of delay of something, or a little bit of storage corruption.
Anything.
Exactly. And that's where things get really fun. I mean, that's what makes distributed systems hard and maybe less predictable than people would actually like. And so modeling those things, figuring out how to model them, first of all, let alone diagnosing the outcome of that once you maybe inject a fault and you observe the behavior, and then like, okay, well, where is the root cause? Where do I have to fix it in the source code? I think is like a very challenging thing, and frankly fascinating to see the collective team all work towards that and having the appropriate tools to make that happen. So,
and a lot of that testing is happening automatically these days. So the DevX team came out with a really great tool that does exactly that, does a lot of chaos testing. It runs regularly. We get email reports daily about things. The performance aspect, there's another tool set that we have that monitors various benchmarks as we commit things to the repository over time. We're watching graphs go up or down to see, whether things are positively or negatively impacting performance. They're happening daily, sometimes even more than that. It would be a fascinating metric, actually, to really properly measure how much CPU time we spend in a day just running all of these.
Yeah. I do recall Derek Collison sending out a tweet last week, I think it was, and he goes, the Nats test suite ran 117 hours worth of unit tests in a single day or something because of the parallel jobs. And that's just like, and that happens all the time. It's just like constantly running these things, every commit, every, PR, everything. And then that's what's like on, public GitHub in terms of the unit test. But then we have all of the other kind of background stuff that we're working on that's trickier to integrate with GitHub Actions, for example.
Yeah, and what's worth mentioning that each of these tests, even if we call them unit tests, we are actually spinning up whole clusters, super clusters, dozens of servers that form the clusters. And even despite those 150 hours, we still have other, as you mentioned, right, other ways to test it. And usually when you test software, which is not a distributed software, the latency introduces latency delay and performance degradation. That's the most common thing that happens. But if you start working with consensus of any way, suddenly a whole new set of problems appears. That the problems can surface if you have high latency or low latency, and each test has to be tested against many scenarios. If you have, as you mentioned, crazy topology, we have to test that some things are low latency, some are high, the jitter is different. And you might think that in perfect conditions it's the least things you catch, but that's also not true, because the amount of variables you have in distributed system, especially in a system like NATS, where you can have leaf nodes across the ocean, which are actually a separate cluster, and here you have different cluster, and all different network behavior happens that it's very hard to predict. And despite all those hours, it's impossible to test all the cases, all the variables, because it's too much. So we introduce variable, basically all the inputs being variables against which we run, as Neil said, hundreds of tests, sometimes more, not only unit tests, but compound tests that try to do normal things and break things in behind. Like break some cluster, break some connection, split the network. And if you think about how many variables there are that you can tweak and change, that change the outcome of the test, it's I think that the hardest part is to actually reproduce the error, not to see the error, but to then correlate it, which set of inputs causes it, so we can reproduce it in a repeatable way. So, and then fixing is very simple, despite code base being huge. But having this reproducible example with all those various inputs set in a specific settings, it's the moment of, yeah, we gotcha, and now we can fix it and move on to the next one.
And we still get thrown curveballs occasionally, because you might even think you've got a simple 3-node cluster, and you'd think that the latency between any of those points would be the same, but we have seen cases where that's not the case. Traffic between nodes A and B is significantly quicker than traffic that goes from A to C, for instance. And, distributed systems that are trying to maintain consensus have to deal with this. So we can pull out these test scenarios from all sorts of cases.
I think, and on that point, I think one of the things that is unique to NATS, but also challenging in terms of debugging and testing, is the fact that a NATS topology can be in a heterogeneous environment. It doesn't, a typical, distributed database, other streaming platforms and things like that expect to be deployed in, a cloud environment with super fast links between availability zones, sub-millisecond, or across regions that the latency is a little bit more predictable. And so this environment that this system is actually running in is nice and it's clean, and not that you can't still have problems, but it's way more homogeneous than environments that NATS gets deployed in. So we have clusters, super clusters that can be deployed in a standard cloud environment. But then we have like leaf nodes like running in cars. We have on random edge devices in factories, on oil rigs, things of that nature. And like that completely changes all of the kind of the whole situation in terms of like, well, what actually was the problem? Did a message get dropped because a link was down or something? And debugging that is just crazy. So I think it is one of those things where, because of NAT's flexibility and the sort of topologies that people design for their use case, it introduces a lot of complexity in debugging and addressing user and customer needs in this case. So that's a really good point.
Yeah, and when we talk about why it takes so long to get a release like 2.9 to be, more where we want it, and we get a release like 2.10 to be to the point of, stable that we're happy with, this is ultimately it, isn't it? There are all sorts of parameters that go into good testing. We like to think that we're trying to cover as many of them as possible. I think in reality, you never get to 100%, but there's a lot of effort that goes into QA. We're spending the time.
Yeah, and to add on top of it is, because of how we talk a lot about topologies in NATS that can span the globe and being clusters, superclusters, and leaf nodes. But what adds to it is, one of the great features of NATS is that topology is very elastic. And we see that each user have totally different setup, totally different topology that we didn't even anticipate somebody could create, which is a funny story about the leaf nodes being used for those IoT use cases in the first place, because they were not designed for it, and now it's their main purpose. But how many topologies you can have, how different they can be, it only adds to that complexity to have all the cases, even not even tested, but actually just recognized.
Yeah, I mean, leaf nodes actually are a really interesting sort of way of extending a NATS system. I don't think it was ever envisaged when NATS was first created that systems would extend just naturally in that way, that you just think, oh, we need to extend over to this location or via this link or to this device. And leaf nodes are just a really natural way of doing that, and the NATS system just extends with it. That's incredibly powerful.
For sure. So to quick wrap up this section, because I know people are eager to actually hear about 2.10 things. So what, just based on all of the new testing strategies or tools that have been adopted, do you either of you have sort of your favorite that you're been exposed to, and or maybe the reports that you get for some failure, and it's been really useful as a tool for you to kind of dig into the source of the server?
I would say that we've been rescued more than once by having good performance data, by having the benchmarks running pretty much daily, watching how things move between different commits, because we make changes, and you'd like to hope that most of the changes that we make are helping us rather than hindering us. But occasionally something sneaks in that behaves but is a bit slower or might defy user expectations somehow. And I would say that just having access to that performance data just naturally has been really, really useful, especially because the number one thing that most customers and most users come to us asking is, how do I squeeze the best performance out of this system?
Any thoughts, Tomasz?
Yeah, I think that one of the tools that help us a lot is the one that allows us to, when we get into cluster into a specific state, we can just go back in time and see the state when it happened in some way. And I think that this was surprising the chaos testing that basically wreaks mayhem across the whole and topology in very random way. You look at the tests and they're very simple, but when you add this chaotic element, different chaotic element you add, like latency, like jitter, like shutting down stuff, separating the network surfaces, different errors. And it's not only on the server side, to be fair, right? We realize that a lot of time when you shut down the servers, it's not the server struggling, it's sometimes the clients, because the clients suddenly have no idea what's happening, something disappeared, and they try to be smart and reconnect. But we see they're not doing it quick enough. We found also those issues. So this part, I think those tests emulates in a really nice way those edge cases we see in our customers and users. Because one of the first things we ask when something breaks is, did something happen on your network that day? Did something happen with the VMs, whatever it is, right? Because those things, of course, we should recover. The nuts should recover, but knowing what triggered the issue is very important. And those tests that introduce the different chaotic behaviors really help that. So we can see it first before somebody reports it, and we can have the edge condition fixed before it happens for any user.
For sure. Yeah, that makes complete sense. Yeah. It's always, what happened? Is there anything you're not telling us? It's like, what is that called? The butterfly effect, that, butterfly flaps their wings and then it causes a tornado somewhere else. It's like, understanding the cause, root cause is really tricky, but you can at least start with some correlation to as a starting point. So yeah, that's great. All right. So transitioning from that, now we can kind of get into some 210 things. So I think a good framing for this, because I think with any release that, takes a year or has intention behind it, it's good to sort of frame it in like why, what ultimately is the decisions making that goes into choosing which things land in a release like this and what maybe doesn't. So I would say three themes that we sort of gathered that I'll just rattle off, and then we can maybe step through each one, talk about some of the things that have been implemented in 210 that support these themes. We have increased scalability. We have a new point of extensibility that we'll get into that I think a lot of people are excited for. And then we have predictability. So that's been I know predictability has been, and we'll get into what those maybe concretely mean, but has been a big one, and actually I would say one of the main drivers for all of the 2.9 testing leading up to 2.10. So, and maybe you could throw in stability as well, predictability, stability. So I know, Neil, you have done a lot of work on this sort of predictability side of the fence, in particular with tail performance and the storage and handling, as we sort of call it internally, these millions of interior deletes problem with, KV buckets that people are using, putting in and deleting hundreds of millions of keys and things like that. And as Tomasz said earlier, it's like, we don't, this is a tool, we put it out there and we have no clue that people are going to abuse it and use it in certain ways. And so when people keep pushing the threshold of what it was originally designed for, you run into unintended, performance hits. And so I know Neil is sort of our resident performance expert. So you want to share a couple little anecdotes or, things that 210 has received to help with this?
Yeah, I mean, what I think we've had to consider really is that some of our users have outpaced our expectations on scale or on throughput. That's natural when, especially with a project like ours, where it goes out into the world as open source, and like you say, it can be used for anything, anywhere. And we spent quite a lot of time looking at the actual storage architecture that underpins Jetstream, because we have to be able to not just maintain a decent publish throughput, that applications can publish into streams and not find that they're jittering or creating back pressure when they shouldn't, but also that you can pull data back out just as quickly. And the interior deletes is actually really a fancy name for a simple problem, which is that we're storing things in order on disk. And if you have limits or you have something that affects how much data you retain, that we might then end up with, you've got some data right down at the beginning that you are interested in keeping. You've got a huge gap in the middle because all of that stuff was processed, or it's been, you've no longer decided to retain it for some reason. And then you go but right up to the head of where you're currently publishing, and you've still got this, this stuff that you're interested in. And it's how do we deal with not just handling the massive amount of state that we have about all the messages that we've deleted for whatever reasons, but how we manage that when we're compacting blocks down, or when we need to go back and fetch messages that are older or newer, or we want to seek back to a specific point in time. So the old method for this was really just that everything was stored in a fairly straightforward, orderly fashion, and we held quite a lot of information in memory about whether or not we're retaining something or whether it's been deleted. And then in order for the consensus to work, we would generate snapshots. And these snapshots are basically a description of that state. How many messages have you got? How many have you deleted? Which messages do we no longer care about? Which limits are we enforcing? And they get replicated across nodes so that if something goes wrong with one node and it has to transfer leadership to another, that another node can just take over. And what we found, actually, one of the biggest problems that we found was that if you end up with a really large number of interior deletes, a really big gap in those data structures, that the state snapshot for the messages we're retaining and deleting ends up being really big, because it's tracking more information about things that we no longer want to keep compared to the relatively small amount of information about the data that we do want to keep. And in order to send that to other nodes in the cluster, we need to marshal that down into an intermediary format. And we were finding that more and more CPU time was going into this process. And the server is backing up behind that work. So straight away, we're thinking, right, there's got to be a better way to compress this information down into a way, one, that we can marshal more quickly, and two, that we can get into a smaller form so that when another node receives that information, it can act on it either just as quickly, if not faster. So really getting down into the roots of the file store has been a really big part of this release. And when we talk about the performance gains that we're seeing, most of them are due to this work.
Yeah. And just for people who maybe aren't as privy to sort of this, I would say, unique characteristic that Nats provides with streams, which most people think of, streams, topics, other streaming type systems where it's a depend-only type of structure, and then there's typically compaction on sort of the back end of that. And that's really the extent of a lot of these other sort of append-only type of logs, for lack of a better term. Where Nats is a little bit unique with that is that you can actually explicitly delete an arbitrary interior message within a stream. And so as Neil noted, like this is how, frankly, the KV abstraction actually works, being able to delete messages, tombstone them for what it's worth, and being able to then, clean them up on disk over time. And all of that metadata needing to actually mark a message that it's deleted, and you need to carry that around so that a consumer isn't, delivering that to an active client or something like that because it was proactively deleted. So, or the expiry, the limits.
Yeah,
yeah,
we talk about this as well.
It.
We use the language of streams obviously quite a lot, but KV buckets are streams. Object stores are streams.
Yep.
So everything benefits from this.
Yes.
Just being more intelligent about what we put on disk, what data we're sending around the cluster, how we represent this information. I mean, we've tried to use two different methods to improve this rather than just having one great big long sequence set of messages that you've deleted. We've tried to use AVL trees for what is effectively quite a sparse set of deletions. And then we also use run length encoding for when we've got quite large blocks of, we've deleted this entire range. We don't need to preserve anything in this range. And that allows us to store quite high fidelity in much less bytes effectively. And the NAT server will try and use whichever structure it thinks is most appropriate for the pattern that it sees.
And I think that interesting context to that is that those things, we didn't care about them that much, especially in theory deletes, because as I mentioned in the previous episode, we advertised a key value, for example, like, oh, you have streams, you have JStream, you want a simple, small key value storage because it's convenient. Here you go, it's this API we provide to you. And then a year later, a user comes in, how about 10 terabytes key value store span across the whole globe? Will it work too? And I think this is what led to this.
Yeah, and the thing is, it worked. It's just, we needed it to work better. So that's where a lot of the effort went here, is how do we improve the file store and the underlying engine effectively to handle this sort of scale.
Yeah, and I think that really speaks to sort of the pragmatic approach that the NATS engineers frankly bring, which is like, you put something out there intentionally being conservative to sort of prove out a use case, to say this might be a good idea. Like, we have a stream, we can model a KV on top, and that's when people just run with it. And then it's like, you're not going to over engineer something hoping someone's going to scale to 10 terabytes out of the gate. But the fact that you put this out there and it's an accessible abstraction and it's already baked into NATS, you don't have to have another external dependency to rely on. People will use it, and they will use it quickly and aggressively. And then that's when reports come in and they're like, oh, by the way, I'm trying to do this thing, and it's a little slow, or it's not scaling as I expect. And then we step back and we're like, holy cow, I didn't even expect that. And that's that whole lovely feedback loop, as with most projects have, but with NATS, because it is so flexible, because you can do so many things, it's a toolkit for people. We're constantly getting new use cases pop up and new scale requirements, and it's frankly fun. It's terrifying and fun at the same time, I would say.
I think
it's like, yeah.
I think what really makes it terrifying, and what accelerates the scale where people adopt our new APIs, is the fact that many of our users are using NATS as a connectivity layer for the whole infrastructure, which means NATS is everywhere in their company or in their use case, in their infrastructure. So when they see a new feature, they want to use it across their whole setup. And with the scale they use, which makes it that people adopting those new APIs, they immediately, test the API, does this fit our needs? Oh yeah, so now terabytes of data across the whole globe, which makes it reach the new boundaries much quicker and in much more aggressive way than in many other toolings, when the scale is a little more growing, a little more slower. For us, the new API just blows up almost immediately to the level where our other APIs are used.
Yeah, and it's important to us to make sure that we're staying either caught up or ahead in that regard.
Right. So that was Tomasz, you're really good with these segues. But one of the second themes that we wanted to touch on is scalability. So we've already sort of alluded to that a bit, but there's some, I would say, explicit features that are out of the box. You don't have to do anything, they just work, but they're definitely worth digging into in terms of, and I don't want to spill it just yet, if either of you want to take the first one on the list of, as we call it, V2 routes.
This is an interesting solution to a problem that you really don't see unless you get to a certain scale, which is, we are using TCP connections to connect cluster nodes to each other. And we are also a multi-tenant system. And in addition to just application traffic as well that users and customers are bringing, we're also running quite a lot of internal traffic, for example, for Raft consensus, which is also built on top of NATs. That all of this has to be sent between nodes. And what we don't want to happen is that application traffic gets stuck behind consensus traffic, for example. Equally, you don't want the consensus traffic to get stuck behind application traffic. You don't want two separate accounts to, you don't want one to be able to cause a denial of service effectively to another. So the model up until now has always been that these connections between NAT servers, we just have a one-to-one. Effectively, between any pair of servers, there's a one-to-one connection. V2 routes is about changing that model so that instead of just having the one connection, we have multiple, and that the NAT server is intelligent enough to either assign these connections so that accounts are just naturally put onto their own routes, or that the administrator can make that decision explicitly and say, look, this specific account is one that we care very deeply about having low latency, for instance, or not being affected by header blocking, therefore reserve this one connection. Because obviously we're at the mercy not just of what's happening at the physical network layer, but also TCP congestion control, particularly in cases when you're working over the big I internet, as we like to call it, where really all bets are off. If you're going between cloud regions or different data centers, or even if you're just, if you are extending out to places where connectivity isn't quite as good or quite as reliable. So we've spent a lot of time thinking about how to avoid that problem. And we see some quite nice gains with this, actually, that consensus stays up to date more quickly, that application traffic makes around the cluster faster. It's been a nice change that actually, if you want to just leave it alone to do what it does, it works out of the box.
Yeah, no, that's a great explanation. So just to recap on that, so out of the box with 210, you literally upgrade, no new configuration required. There are knobs to turn if you choose to, but out of the box, rather than having one TCP connection between each pair of servers, there's going to be a pool of TCP connections that are shared across accounts. And then importantly, as you alluded to, as we call it, the system account, which handles all the Raft traffic and all this sort of, non-account, non-application account traffic, that's going to have its own dedicated TCP connection out of the box as well.
That's right. Yeah.
Nice. Yeah, that's fantastic. And just to sort of roll in, and I would say another use case that has been popping up among customers, at least that we've been seeing, is this notion of a stretch cluster. So other than, and we'll get into that in a second, but other than simply the observation that under a certain level of load, the header-line blocking and, we want to be able to try to parallelize that traffic was one obvious need. But the other one that's interesting that sort of flows into the other bit of work that's gone into the routes as well as leaf nodes by happenstance is this notion of compression as well. So how does the relationship of stretch clusters and compression work in this increased scalability effort?
So I'll talk about compression individually first, because that's something that merits a bit of explanation by itself. So a lot of information that flows through these systems, quite often a lot of it has similar structure or is quite similar in nature, and compressing it is giving us just a way of sending less bytes over the wire generally. And we're using quite fast compression algorithms, so it doesn't really cost us too much in CPU overhead, but what it gives us is much more headroom on the network, so that, if you are in a situation that the connection's not quite as fast down to a leaf node as that you'd hope, or if you are sending slightly more information than you might normally get over a pipe if you were sending it uncompressed, we're effectively negotiating that for free. And we're doing that over route connections and leaf node connections automatically at the moment in 210.
That's great. And I think one of the things that we won't get into all of the ways you can configure it, but one of the really, I would say, and I know clever to some people might not be a good word all the time, because you want to be obvious and deterministic, but a really good design, I would say, let's put it that way, is, as you said, this mode that you can configure with compression for routes and leaf nodes. And in fact, it's by default for leaf nodes, because it's the assumption that you're going to be over a longer distance, and the network might not be as reliable, or the latency might change more dramatically. It's this notion of this sort of, like, as it's called, S2 auto, not that matters right now, but it's this idea that there's actually thresholds for the degree of compression that is applied based on the round trip time from, let's say, server A and server B. So if that changes over time, the degree of compression will also change with respect to that, which I think is really interesting to say. You sort of tune the dial up when you need more, and then you tune it back down if you happen to have really good latency, and it just sort of works out of the box like that, which is quite nice. And there's other modes as well if you want to be a little bit more explicit with, the compression level and things like that. So, but I thought that was the design that has gone into that has been really interesting and nice, and I think is going to, again, going back to our arbitrary topologies that people come up with, they're going to have this degree of control now when they need it to, tune the level of compression, or just rely on the auto compression to kind of handle it for them, which I think is great. Which then gets into this notion of a stretch cluster, which I think would be as a use case where these particular features are very supportive of. And I think it's, again, a little bit unique to NATs, in the sense that, clusters, as people think of in distributed systems, are typically scoped to a region. NATS has this notion of a supercluster, which can span multiple regions, and you can connect, and you can keep stretching it. You can keep growing that cluster out to sort of across regions. But then we started having this pattern pop up for customers in particular that we've been calling a stretch cluster. So what is different about a stretch cluster versus our kind of typical cluster or supercluster language?
Really, the stretch clustering is where people are just taking the regular clustering mechanism and pushing it across zones or across regions, sometimes even across data centers. So where on the one hand, you might have a pattern that you have 3 times 3 node clusters that are connected using the superclustering mechanism. The alternative is that you just have a 9 node cluster. And it's the fact that it scales out of a specific location is what we refer to as the stretch clustering.
And why would one want to choose a stretch cluster over, let's say, a supercluster?
I think it's more easiest to see, because the supercluster has this advantage that you don't suffer that much of latency between the regions, because each jetstream group is only bounded to this specific cluster in a supercluster. So it does not suffer, your general performance does not suffer for persistence layer with Jetstream, does not suffer because you have more regions somewhere else. And so for this use case, that's totally fine. You have still in supercluster, the global connectivity, everything can talk to everything, but data is localized in a specific set of nodes, which are in a specific cluster. It's very performant that way. You don't suffer the increased latency, the spikes of latency between the regions, or even cloud providers, or continents. But you might have different requirement, especially in some regulated ecosystems, is that you actually need the data to be replicated everywhere. And you can sacrifice some of the performance because you can gain out of the box almost, fitting the regulations of whatever industry you work in, because your data, it not handles for you that the data is available in consistent manner everywhere you need it to be. And yes, you can achieve something similar with superclusters, but then you need to include some mirroring and sourcing, which is a very powerful feature in itself. but the guarantees around when the data will be available, its consistency is a little different. It's synchronous in nature. So it is a little different use case. And those are, I think, that the most prominent differences when you would like to go to the stretch cluster is when you are okay with suffering some of the potential performance because of higher latency, but you get the data replicated however you like. And it's worth mentioning here that you can actually tag the servers and say what data lands where, which can be very powerful feature. Or you can just say to NATS, yeah, just do how you think, as good as you think. And I think this plus the compression to get to it to a second, which I call it kind of adaptive. And we always were saying that NATS is an adaptive architecture patterns. You can do a lot of stuff with it, with the leaf nodes, hubs, superclusters. So the extended clusters is, again, once, as Neil said, it's not a new thing in itself. It's rather a new pattern that emerged from our users and their needs. So it's getting NATS becoming even more adaptive in that manner. Shout out to our tests that will have even more cases to cover. But yeah, I think that's the most important thing, that it covers the requirements of data being stored in consistent way in many regions, many whatever you call it, cloud providers, regions. Yeah.
And the thing is that this hasn't required a significant re-engineering on the parts of NATS to support this. This is the great thing, is that extending clusters in this way is a natural operation, but being able to support the multiple route connections to reduce head-of-line blocking, being able to support automatic compression to try and give us a little bit more headroom on the network, those are the things that make it a much more feasible pattern for a wider range of applications.
So we became more 100%. Durable resilient against different conditions that then occur across the network, let's say this way.
And so just to recap that, so you can have, again, there was no inherent limitation before that NATS can do this. So you could have, 3 cloud providers, 3 different regions, a 9-node cluster deployed. We have server tags, you can place replicas, have anti-affinity on stream replication, things like that. But really sort of these V2 routes and these compression really makes this type of stretch cluster more performant. It's optimizing it in certain ways. And again, the driver being really these use cases that are for regulatory reasons or what have you, or they want to, tolerate regional failure, like entire region failures versus only a availability zone or something like that. So again, it goes back to what we had said before, which is, KV bucket with 10 terabytes. Okay, people are pushing the boundaries. People want to stretch a NATS cluster out across providers and regions. Okay, well, let's figure out how to sort of optimize the network for that particular use case. So I think that's a trend that maybe people can take away from how we make decisions around what goes into NATS. So final theme, let's quick touch on extensibility. So what does that mean with NATS? Has there ever been any extension points other than leaf nodes? We'll caveat that for a minute, but in terms of extending the server in a certain way, what does that mean in this context? Any takers?
Yeah, I can start. I think it's hard to start to discuss this because there's so many ways many angles you can approach it. But I think that as we can say that NATS with every single release becomes more adaptive, more extendable in terms of topologies and the ways you can, set it up. It was a little different from the perspective of plugging in something into the NATS ecosystem. Yes, you could very easily, because the NATS protocol being so easy, I think it's quite easy compared to some other APIs to plug in some kind of connectors, whatever other things you can interact with from NATS or with NATS, but we never have built-in extension point for NATS. And one of the most asked thing was, that yes, NATS has great many ways to do security for authentication, authorization, distributed, non-distributed, server configured. So many ways to do it. But we're asked a lot about being able to plug in. I want to plug in my own auth, whatever it is. And I think this is the first step to extensibility that we were taking, but probably far from the last, because we found it pretty nice to use. And what it means is that NATS now allows you on specific subjects, without getting into the details of it, to okay. Sorry guys, I have to cut.
That's cool. That's fine. We have kids in the background, no problem. So yeah, I think just to that point, yeah, it's sort of that first extension point that you could plug into the NAT server in a way, and the authentication and authorization call out, as we're sort of referring it to, is that sort of first step in that direction. So Neil, did you want to sort of touch on just the basic maybe flow of how it works?
Well, it's really the sort of motivating factor to this was that we've seen customers that have come to us with these absolutely giant authentication schemes tracking countless numbers of users or applications, and the call out is basically a way of the NAT server reaching out to an external service to say, hey, I've got this client connecting. Should it be allowed? What should it be allowed access to? Rather than having to track all of this in very large, very static, very difficult to manipulate configurations.
Mm-hmm. So the flow is like you establish this client connection, and the server is basically delegating, giving a payload metadata about the client connection, maybe the credentials that are passing through it, and then the service. Yeah, and the service can basically say, hey, I need to talk to like LDAP. I need to talk to OIDC of some kind of backend that implements, or it could be a file on disk. Frankly, it could be, a little SQLite database or a file. But the point is that you have now control over saying, given these client credentials that are being passed in, you can validate it against your own, as you said, authentication scheme. And then what gets returned is obviously yes or no in terms of is this client authenticated, but then you also have this freedom to be able to dynamically generate, permissions, NATS permissions that NATS will then understand on behalf of that client connection to say, yes, maybe at this time of day for this particular user that's trying to authenticate, they have this degree of permission at this time, and you have control now dynamically on the fly to generate, these JWT claims or these permissions that actually would be used for the duration of that client connection session. Is that reasonable?
Right, because ultimately most organizations have already got an authentication structure in place. There's a lot of companies out there using LDAP and Active Directory. There's certainly lots of organizations out there with various different types of single sign-on, and these callouts are really the first way of integrating with those pieces of infrastructure in a way that makes sense for NATS and for outside of it.
And I think like you said, we won't get into because it's made this mistake last time of trying to describe code, but on a podcast. But I think one of again, design is really important, and keeping things simple is really key, sort of in NATS in general. But I think the mental model is, as you said, you have the service that you spin up. It's listening to a particular subject that's sort of predefined, that the NAT server knows where to sort of delegate request a client connection coming through. And then it's literally just another NAT subscriber, right? And then it just responds. So it's not like a new protocol. It's not a new, it's really just, it's still just using core NATs, which is beautiful.
I think it continues the pattern of building on top of core NATs. We do it ourselves.
That's what I wanted to say, that you can use a recurring VM with it. You can say it about about every single API that after, if you dig deep enough, it's always just pops up.
Yeah. Yep. That's right. Cool. All right. So So these were sort of the themes, which I think are good, and there's a bunch of like features and development that have gone into those. Let's touch on, and I'll just defer to both of you. You can pick, two or three other types of things maybe that maybe don't quite fit in those buckets, or things you're excited for, or you think users would be excited to hear. What are a couple little features that not little in effort, but little, in simple new features that people can leverage, even though some of them have been quite extensive in the design and implementation side of things. But what would you maybe choose to share with people?
I'll call out two particular things. One is around stream compression on disk, and this is another change that we've made in the file store. Quite often, users and customers are coming to us because they want to be able to compress their data, but they're also needing to encrypt it. And obviously, if you enable encryption in Jetstream today, pretty much all of your compressibility on the disk at the file system actual block level just goes completely out of the window. So the compression at the file store level is about compressing the data before it goes through the file store encryption, which basically means that you can mix the two in a way that actually makes sense, because if you try and compress the encrypted files on disk, you're not going to get very far. And the other that I'd like to make a mention to as well, because this is really a bit more of an integration point, I suppose, to existing infrastructure, is MQTT, with the addition of what we call QoS 2. So for anyone who's familiar with MQTT, there are different service provision levels. There's QoS 0, which is at most once delivery. There's QoS 1, which is at least once delivery. And QoS 2 is about exactly once delivery. And the reason that we've spent a bit of time on this is because there are applications out there that care about this. We quite often hear from people, one of the big projects that comes to mind is Home Assistant, that uses MQTT integration, relies on QoS 2. So by continuing to put a little bit more effort into these integration points and into MQTT support in particular, we're making this really great entry point for people to start moving these workloads onto NATs, especially if they're already using NATs already.
Yeah, for sure. That I know that's been high in demand, so that's great that's been integrated. And again, for people who maybe didn't even realize that MQTT support is out of the box with NATs. So you literally have a config block in your server config. You open up the port, and then MQTT clients can talk to, use basically NATs as a broker, MQTT broker, and there's transparent translation from MQTT topics to NAT subjects. And so you can actually have different clients on either side talk to one another, which is really great. And so for the use cases where it's like you have these devices, they already talk MQTT, but you want your whole backend to use NATs and use all of the other constructs, it's a great integration point without needing to run additional infrastructure to bridge those two things.
Especially where that equipment or those clients might be embedded, or they might be industrial, and they don't ever stand a chance of talking anything that's not MQTT, but you still want to be able to bring them into NATs for the journey. That's a really powerful point of integration. So we've been spending more time on that.
Yeah, I think it's also at Vim we have that, if you already have NATs, by the way, you also have this and this, and MQTT and WebSockets are probably the most things that pop up in those examples. Yeah, and from my perspective, there are two things, two subjects, both related to subjects. One of which is that the consumers that you create on stream, so what we call the views into the stream, now supports having multiple consumer filters, because as in consumer you cannot specify any filter, meaning you basically consume the whole stream and every message it's there. But NATs, being flexible as it is, allows you to filter out some of the data to a specific subject with support to wildcards. So for a long time we thought it's enough, right? Because the wildcards are pretty powerful to narrow down what you're looking for in the stream. But with time, with more use cases and more complex subjects architectures, I would say, how you structure your subjects and your data, we realized that in many cases people needed to create many consumers to get this one specific stream of data, which is not only not perfect from optimization point of view for the server because it has to care about more consumers, but it also makes it much less nice user experience because you have to start to handle the order of the things that arrive for each consumer separately, and you can pretty quickly reorder them, but it would be nice if you don't have to. So that's what we added into the 10, meaning it's a consumer can have many filters, which solves quite a few issues that force users to have multiple consumers and then reshuffle stuff. Or if you wanted to get some subset of the data for a specific token in the subject, like in the second token, you have the factory name, for example, and you don't want to have factory 1 or 2, but you don't want to have a wildcard because you're interested in, like, I don't know, first 5 or first 10. So this solves this problem and quite a few more, but basically you don't need to create many consumers for the use cases when the wildcards were not enough and when subject filtering was not enough for you. And you don't have to care about the order also to reshuffle the stuff because you don't have to merge data from two consumers. Second one is, I think it's very powerful. It's a aha moment if you know how nuts works, but it's a little harder to explain otherwise, which is that nuts for some time, I guess since 2.9, supports subject mapping, meaning that for the server there is some incoming message on a specific subject. You can still configure the server that it will map this subject to another subject. And that was powerful in itself, but we realized that it's used a lot. It's a core nuts feature, but it's used a lot in cross-account communications, import and export, especially in complex topologies when maybe the key value is on some other leaf node on the other account, and you export it from, again, like this factory and that factory. They have the same subject, all of them, but you want to aggregate them differently, and that could be done more or less with the subject mapping on the server level. But it's much more flexible and powerful right now when the subject mapping can happen on the level of the specific stream. Meaning you have a superpower on the stream level over what's happening to your subjects. It allows you to many things. It allows you to even handle, I don't know, switching subjects for API changes without any breaking change, or you can get data from many different places, streams, leaf nodes into a way which is not you don't have to compromise your subject structure and architecture you had before. Now you don't have to, because you have full control over it on the stream level. So you can have very nice, clean overview of how the data is structured for your stream, and then by extent how you can use this data and filter it. So, but that's only half of the story, because it gets even crazier. Because right now you can have also those mappings on the level of the mirrors and sources, which, if you think about, again, especially things, not especially, but the key values, I think the simplest example, when you can suddenly very easily, without any hacks or hard work, have an aggregate that aggregates data from everywhere in a very nice and consistent and clean way, construct your new view into everything. You can discuss it in so many ways that I just picked those examples. So yeah, the recap is you can have subject mapping on stream level, sources and mirrors level. I think it's incredibly powerful, especially when you need some kind of behavior like this. We spend a lot of time with our users and ourselves when creating those vast topologies. One of the most challenges sometimes were like, okay, so how we now just get all the data together in a way that makes sense, that's explicit and that tells what it is without much of thinking about it. And it was one of the challenges that I think were sometimes unexpected for everybody and for us included, that as the topology grows, the subjects are becoming harder to work with. Doesn't matter if inside one account or many accounts, if you have the intersection points, it was getting harder. And this removes a whole, I think, category of problems and solves them because of those possible mappings, while adding a whole new set of possibilities you can work when working with streams.
It's also a bit of a natural solution to a problem which I'm sure people run into probably quite often, which is that if they're bridging more than one system together, it is subject namespace collisions. That you can now just rewrite these on the fly so that you don't have to worry about whether you're polluting one namespace with another.
Yeah, that's a great succinct point. And I think I sometimes conceptually think about it as like equivalent to how, core nats, pub sub, you can do fan in and fan out, and you have this ability with streams in a way to say, can I apply subject mapping or subject transforms, as it's more sort of generically called? And no matter sort of what the, let's say, ingress subject is coming into a stream that's sort of fanning into a stream, either from, other mirrors somewhere else or other source streams, you can choose to basically say, well, this is what I want my subject hierarchy to look like, from these streams, incoming streams, similar to how exports and imports work, where to avoid namespaces, or you just maybe have a preference in your particular application or your domain, you want to be able to change what you want the subject hierarchy to actually look like. And you now have this adds more control over being able to do that, which I think is really good. So, and again, it's one of those things that it's like, most people can probably ignore it for right now, but once you run into something and you're like, I would really like to use this, then you're going to be thankful it's there. So that's great. Cool. So we went over 4. There's plenty. We have a whole 210 what's new guide for folks to check out. So definitely a lot more features and bells and whistles that you can kind of look into. I wanted to sort of end and maybe ask a question just to get your thoughts. No pressure, no requirement to answer. But now that 210's out, and what does the future hold? What are we looking at for maybe 211 or beyond?
Ultimately, we're continuing on this trajectory, aren't we? We want to be ahead of scale problems. We want to be ahead of stability problems. We want to be ahead of predictability problems. And 211 will be, more features, sure, but it will be a lot more effort in how do we get nats and Jetstream and everything else we want to build in the future to scale up to where people need it to go.
I think it's critical what Neil said, and it will be boring, sorry, Byron, at the same answer. But I think that, as I mentioned in the beginning, or somewhere in the middle, is that many users are using nats as the backbone of their whole infrastructure. So it's a critical element of their whole setup. So we really want to give them as stable, as performant, as predictable tool as we humanly can, as we are able to. So we're pushing ourselves, and we will keep pushing ourselves for 211. As Neil said, to be, if you're ahead, it's much easier to keep up. If you're in the middle of user expectations, and people learn pretty quickly, you can scale to terabytes, and it's so easy to just put one more zero at the end, not so easy to support that one more zero. So it's getting harder and harder to be ahead of the expectations. But that's why we keep pushing, because more ahead you are, the less stressed the system is, the more predictable it is. So yeah, I think this is one of the most critical things in Nuts ecosystem, is that users, they might miss this feature or another, but they want to be sure that everything they use while using Nuts, they can be confident that it will work just fine. it will recover, and it will act in a predictable manner so they can trust it and run the whole company, whole project, or whatever it is on it.
For sure. Yeah. Wise takeaway with that. So any final thoughts in general? Anything to review on this episode, or any final takeaways?
Just that there's lots of really interesting stuff in the changelog. Have a look at it.
Right on. Cool. Well, thank you so much, Neil and Tomasz, for coming on. And sure. And for everyone watching or listening, please leave a nice rating, comment on YouTube or your podcaster of choice. And we'll catch you next time.